Okay, so we are well, let's lower the indices. Let's just make them A and B. RAB minus R over 2, the metric GAB, is equal to some constant times TAB. That's the field equation for general relativity. So, for example, here's one component. So we choose 0, 0 for A and B. We get R0, 0 minus the scalar times the G0, 0 component equals K times T0, 0. That's some kind of differential equation, and we need to solve it for the metric terms. So we're answering the question, what are space and time like, right, in different regions? So in other words, what is space-time like? And that means finding that quantity. So that's the solution to these equations. So we're going to see that this one component, as other components are as well, they amount to differential equations for the metric terms. So we're going to start with the simplest case, which Schwarzschild. Right, so we're going to start with the Schwarzschild solution, which involves certain assumptions to make our equations simpler. So we're going to imagine that we have a distribution of matter and energy, a spherical distribution of matter and energy. It's uniform, and we're going to find, so we're going to think in terms of coordinates that are familiar to us, where we can sort of, that could be a radial coordinate. There's always the issue of trying to interpret these coordinates because the curvature sort of changes things. And so we want to think of trying to make sense of the space-time in terms of time, a radial coordinate, a theta coordinate, and a phi coordinate. So given the distribution of stuff that curves space and time, these coordinates theta and phi should be familiar to us. And the radial coordinate will be somewhat familiar to us, but it will be a little bit difficult to understand what it means in terms of distance. And then the t is of course time, and that should be that should emerge straightforwardly. So we want to we want to find a line element that looks like this. So dxa, dxb, that has certain properties. So it has dx0, dx0 plus g11 dx1 dx1 plus g22 dx2 dx2 plus g33 dx3 dx3. In other words, g naught naught dt squared plus g11 dr squared plus g22 the theta squared plus g33 d phi squared. And so we sort of know what some of these are. So g naught naught, we don't know what that is, but it should be a function of r, dt squared, so we have to solve for that, plus g11, that should also be a function of r, we want to solve for that, plus g22, this should just be r squared, d theta squared, plus this should just be r squared sine squared theta in d phi squared. So in other words, we know that, right, this needs to be time independent. These coefficients need to be time independent. They don't depend on any of the other coordinates either. They're also, because of spherical symmetry, they're also phi independent and theta independent. And we also want, right, so we also know that g naught naught must go to, I guess it's whether positive or negative. If there's a minus sign in front of the t, if our signature is minus plus plus plus, then this should be minus 1 or minus c squared, depending on whether we put c equal to 1. And g1, 1 in that case would reduce to just 1 for r goes to a large value. Let's what else? So what's our project? We want to get, so to get GAB, we need to find the RAB, because we need to solve, we need to solve RAB minus R over 2, this equation GAB equals 0 if we are here. So if we're outside, then there is no matter and energy. There's no energy momentum. Out here, we're in a vacuum. The equation reduces to that. So here's the metric appears there. We'll turn out that this term goes to 0. Well, I guess we can evaluate it explicitly. It'll basically be RAB equals 0. That's the system of equations that we need to construct. So to get these terms, like R00, R11, R12, etc., many of them will be 0. Many of them won't have any useful information, as we will see, but we basically need the gamma. So we need gamma A, B, C terms. We have to evaluate these for a metric that has this form, and so we'll get equations in terms of unknown G0 and unknown G11, and then we'll plug them into this object, which involves further derivatives of this kind of thing. So we have derivatives of the metric. So we have a differential equation for the metric terms. And that's where we're headed.